Started class of the day. We were discussing about electric flux. This electric flux is the measure of amount of electric field intensity passing out of a given surface. So here we determined in the previous discussion that this electric flux will be measured by the letter called phi, and this turned out to be that change in this electric flux out of the surface, which this was a surface and there was an electric field passing through or there in this direction. And if you consider this area, and let's say this area has a positive normal in this direction, that means this has angle with the direction of electric field. This is normal direction, and it has delta S as the surface. So we decided that this is E delta S cos of theta. Or same thing can be written as E dot delta S, where E is the electric field vector present in the region, and delta S vector is called surface area vector. This is called differential because we are using a differential element over here. So this is differential surface area vector. So if a differential surface area vector we can draw on any given surface, electric field will be known to us. The dot product of these two vectors will give us the electric flux, differential electric flux passing through that differential area. And when we go for integration of this relation, we can say that it will be the flux phi that will pass through that given surface or given surface area. It will be integrating this delta S or differential surface area all along the curve. So this is for closed cases. This symbol of integration determines that we are doing this integration on a closed curve. So this is on a complete closed curve. So the flux, electric flux passing through a closed curve, when it is present in E electric field, can be represented by this relation. And here the important point is the electric field which will be given to us this determining surface area vector, that means its magnitude as well as its direction. So you can say that if we have any surface, let's say we have a surface, I'm just considering one section of the surface, and if we are interested in looking at this differential element, so we are considering this to be differential surface vector. Here, the magnitude of this will be simply ds, that means the area that we have chosen. Its direction will be perpendicular to that surface. Its direction is always perpendicular to that surface. and if it is coming outward, we call it as a positive normal. Positive normal. So whatever the angle we measure between electric field as well as differential surface area or the surface area vector, it is between electric field direction and the direction of this positive normal. So if I say that this delta F, delta phi, which I have already written E, delta S, cos of theta. So here, this is point to remember here, theta is the angle between electric field vector direction or electric field direction and the positive normal of the surface. So this will be here theta. That means if we have electric field, let's say in this direction, in this particular example, so this theta will be, we will draw the electric field's direction and we will draw the direction of positive normal, and this angle will turn as theta. And then this will become the differential value of electric flux. Or we can simply say, if we are gone for this integration, here also we will require that angle, so that angle will be also used in here. So anywhere in any other formulation, this angle is used. Angle between electric field direction as well as the positive normal that one has. Now let's take an illustrative example for this formula and then talk about other aspect of this electric flux. This is an illustrative example. Square surface of, let's say, 10 centimeter square area is placed in a uniform electric field of, let's say, 50 volt per meter. Making an angle 60 degree with the positive normal of the surface. Find the electric flux passing through the surface. So, question is this, I am going to read it out. There is a square surface. It has reached its area. So this information is given to us that the surface area of that surface is 10 centimeters square. There is a uniform electric field of this magnitude, which makes an angle 60 degree with the positive norm. So that means the angle which we are talking about is the theta that we have discussed. We have to find out the electric flux that is passing through that surface. This is the question. Now, it is the similar one, the concept we have just discussed. So solution can follow the following steps. We can have a picture, we can draw a picture. Let's say let me try to draw the square surface. So this is a kind of surface from where we are interested in finding out the electric flux passing. It will have its normal. Let's say this is the direction of positive normal. And electric field directed is, let's say, in this direction, which makes a 60 degree angle. This information is known to us, and this is surface area S. So the flux that will be passing through this will be nothing but E into S into positive. This will be the total flux passing through the surface. Putting the values, E is 50 volt per meter, so it's SI unit. S is 10 centimeters square, so we need to convert it to meters square. And cos of 60. Oh, this cos 60 is half, so this will turn out to be 25 into 10 power minus 30. Or you can simply write it as 2.5 into 10 to the power minus 2. This much voltmeter can be our answer. So this will be the answer for electric flux passing through the surface. So here we are using that electric field direction is known to us, surface area is known to us, and we have put the values and answer it with us. So when we have a simple clear-cut surface, you can easily find out what is going to be the electric flux passing over that. Now let's talk about another example when we do not have this kind of simple surface area. So formula was very simple, putting the value during calculation was very easy because we are taking these illustrative examples. The main objective is to understand the concept behind. This is another example. Find the electric flux passing through a sphere of radius r if q charge placed at its center. We are having this question. We have to find out electric flux passing through a sphere whose radius is known to us, and we are also known what the charge it has. So let's try to draw this. Let's say this is the sphere. Okay, may not be so smooth. So there is some charge Q has been placed on it. And we have to find out what the electric flux that is going out from this figure or this arrangement. So let's try to identify it. If there is a charge, then there is electric field generated by that charge. And electric field at any point, which is, let's say, r distance away, because this radius is r. So the electric field at any point, which is r distance away that charge, we write it as E is equal to 1 upon 4 pi epsilon naught Q divided by r square. Now, in this sphere, at all the points which are on the surface, we will have same electric field present. Because all the points of this sphere are equidistant from the point center or where the charge has been placed. So, all the points of this sphere will be at r distance from the charge. And at r distance, we have this amount of electric field as far as the magnitude is concerned. Now, one more point, that what will be the direction? Of course, at all point at this surface, we will not have the same direction for this electric field. It goes directly out or in depending upon the magnitude of the charge. If we consider this charge to be positive, then electric field, let me draw different color, electric field will be in this direction. This will be the direction of electric field, when we have taken this Q to be positive. So let me mention this point. Let Q is positive. If it is not, so it can be inward direction, that's not a big issue. And let's take a differential element at this point, at any point where we are interested. This is a differential element of that surface area, and we call it to be delta S. Now, we have to ascertain one more important parameter, which is called the angle between the two. Of this surface area, wherever we are going to measure this, the direction of the surface area vector, it is going to be outward. That means this outward direction will be the direction of its positive norm. This is what happening at a particular point. If we talk about these quantities at this point, we will have a similar kind of thing. The positive normal vector will be in this direction, and electric field will also be in this direction because of that charge. So that means at each and every point on the surface, the angle between surface area vector or the normal, positive normal of the surface area and electric field is going to be 0 because both are parallel. So here we can write that because of the differential location, if differential phi flux passing, so that can be written as E dot delta S. Since they are having 0 angle in between, or let's say these are parallel, both the vectors are parallel to each other, so we can write them simply E into delta S. Now these I'm just writing in magnitude terms because cos of theta or cos of 0 will become 1. So this is I'm able to write because or as both are parallel. Using this condition that both are parallel, we can just multiply their magnitudes. Now, electric field at this point, at any point, this differential point will be this magnitude. It will be due to the charge present inside. And this is the differential surface area. So let's put the value of electric field. It will be 1 upon 4 pi epsilon naught. The charge divided by e square of the distance into delta x. This is delta phi. Now if we integrate this, or in other words, if we add all these differential surface area of this sphere, after addition of all these differential surface areas, we will get the net flux that will pass through this sphere. Because this is the flux passing through this delta S surface. So if we add all this kind of differential elements across the surface, we will get the net flux passing out. So that means we can add all such differential elements. Well, if we say that we are adding all these things, it's synonymous to say we are integrating all the elements. So integration is just a next step or this extension of this addition of these differential terms. So this will give us the phi, the flux that will pass through this sphere. What this will be? Now that means we are summing all the differential elements across the surface of the sphere. So this is a constant term that can be taken out because it will remain common in all the terms. R is essential that can be taken out. Ultimately, what we are doing, we are summing the surfaces areas only, and other quantities has been taken out. Now, if we sum all these differential surfaces area, ultimately what will we be having? We will be having the total surface area of this sphere. So instead of this, we will be writing total surface area. I'm just extending this here. So this will be 1 upon 4 pi epsilon naught, the charge by r square, and this will become total surface area. And we know what is the total surface area of a sphere. Total surface area of a sphere is 4 times pi r square. So we will be writing it as 4 times pi r square because r is the radius of that sphere. Now here, what we are getting, here we are getting that this expression 4 pi and 4 pi they can be cancelled. Similarly, r square can be cancelled, and ultimately we will lead to q upon epsilon naught. So q upon epsilon naught will turn out to be as our answer. That means the total flux passing through this sphere having q charge at its center. So we can also do this kind of questions when the electric charges are present and we are looking for the flux passing through a particular area, surface area. So because of that charge presence, we will have electric field and we will apply the relation of electric flux with electric field and surface area. Proceed in the following way. We can find out what will be the flux. So this will be the net flux coming out because of this charge q at the center of the sphere. So this is another example based on the concept of electric flux. and answer came that Q upon epsilon naught. Now, whatever we are doing here, we have to follow this kind of linear procedure. After a while, we will be discussing a concept in which we will not require all these calculations. In fact, we can find out this electric flux in a single line using some powerful theorem. So, at this initial level, it's important to understand the basic way of finding electric flux. And then after we will be talking about the theorem and things like that. Let's do one more example and then proceed towards the Gaussian theorem. It says that again we have to find out electric flux, but the surface that I am trying to choose this time is a different one. It says that what will be electric flux passing through the surface shown below. So there is a surface element. On that basis, we have to find out what will be the electric flux passing through that. Let's arrange this like this. There is cylindrical surface which is placed in a uniform electric field. This. And this surface is the cylindrical surface, the cylindrical object which we have given, it's hollow from these two ends, and this is the curvature. So what will be the electric field passing through it? We know in order to do any question related to electric flux, so far we have understood that we have to proceed based on the formulation that we will choose any differential element on the surface of, okay, let me try to make it differently. We will choose a differential element on the surface of the object which is given to us, and then try to find out what is the flux going through this. So let's choose this as our delta S and assume out of this differential surface, differential phi is the electric flux which is passing through, and it is what? It is E vector dot surface area vector. Now, surface area will be pointing as this positive normal will be upward, normally up in this surface. So, an electric field is directed in this horizontal direction. Now, based on this, we will say that the angle between electric field and between this normal vector is 90 degrees. So, theta is 90 degrees. Now we can write this as this differential value of flux passing through this differential surface area as E delta S cos of theta. Further we will write as E delta S cos of 90. We know that cos of 90 is 0. So this will make everything to be 0. That means whatever the area, differential area we have chosen, out of this surface area, there is no electric flux passing through. So to find out what will be the flux passing through from this complete surface area, we can add this or we can integrate whatever we say. So the total flux that will pass through will be summation of 0. We can keep on adding 0 number of times, our answer will remain 0. So 0 will be our answer in order to give the response for electric flux passing through the surface area. So here, in fact, we will have no electric flux passing through this surface of the cylinder. The reason behind it, well, this is the answer that we have to give. Then if someone wants to interpret this answer, we can. Based on this the electric field direction, if you look, it is just electric fields they are just passing through this hollow cylinder. None of the electric field lines are crossing the surface from which we are interested in finding the electric flux. As per the definition of electric flux, it is the amount of electric lines or forces which are passing through the surface we are interested in. So there is no electric lines or forces which are passing through, crossing the surfaces. There is no electric fields passing like this. So since there is nothing like this and the angle comes out to 90, there will be no electric flux passing through the surface. So our answer is 0 in this particular case. So based on the same relation, we are able to talk about electric flux passing through the surface of a cylinder. We have talked about electric flux passing through a sphere and also the central surface, let's say spark plate. Now, after doing all this thing, let's talk about one important parameter which will pave the way for discussion about Gauss theorem related to this electric flux. It's called solid angle. The solid angle we are studying in the context of understanding a very important tool called Gauss theorem. To understand this, I'm going to introduce it in detail. After understanding this, we need to talk about two elements very clearly. The first element is that we have discussed that we must be aware of electric flux. And second parameter or second quantity that is required here is the solid angle. So this is something which are forcing us or making us require to discuss what is solid angle. So let's discuss what this solid angle is about. As such, this solid angle is nothing new. It is generalization of the plane angle. we all are aware of what a plane angle is. And if we can generalize that plane angle to one more dimension or including one more dimension, that generalization will be the solid angle. How one can go for the generalization? Let's talk about. So before we generalize, let's talk about the plane angle first. What the plane angle is? If any curve is given to us, let's say this is the curve we are given to. And if we are interested in finding out the angle this curve makes at the point, let's say over here. So what we do, we join the point, these two points, with the point of our choice. And whatever this inclination or this theta is, this is called the plane angle. So here, what was this? Let me use different colors so that we can distinguish what are the extending lines and what is the surface. So this was a curve. In AB curve, we have joined these 2 points, and this angle which we have got here, that's called plane angle. So AB is a curve, and theta is plane angle. Right. Now, if you want to extend this thing, generalize this thing to make a step towards the solid angle, so instead of having this curve, now let's have a surface. That means we have a surface. Or maybe anything like this. So this is some surface. If one is interested that what the angle this surface extends at any point or given. So what one will be doing to find out the angle that this surface will be making at this point too? Just like here, what we did, we joined the 2 points with that O point. So whatever this inclination came, we call it to the plane angle. Similarly, here we have n number of endpoints, because here we have only 2 points, 2 endpoints, we join the 2. Here we will have n number of points on the surface at the terminal points, and we will be joining all those points to this point O. So we will be joining all those points to this point O. So all these points, if you join, so this will create some sort of cone structure, 3-dimensional. And at that time, what this angle will be there, that angle will call as a solid angle, and we represent it by letter for omega. So this omega is solid angle. Now I am repeating this point. Here I have shown only 2 lines, but there is not only 2 lines, there are n number of lines. That means all the points of the surface border, they have been joined this point O. So this will have a cone-like structure, and at that time, what that angle will be, that angle is called solid. It is very similar to the one plane angle. It's generalized in the sense it was in 2 dimensions while it is in 3 dimensions. So in 3 dimensions, we measure this angle to be as a solid angle. Well, in 2 dimensions, we measure as a plane angle because plane is a 2-dimensional object or this geometry. This is the solid angle. Now, this is just a understanding about solid angle. Now let's talk about this formulation and its use, how we are talking about it. Now, if we say that this AB is termed as arc, right? And if we say that arc, this is called arc. And if we say that this arc is of length L, and these points that we have joined is of, this is called radius, so we call it an arc. So here, in plane case, you can measure this theta as the arc length divided by the distance from that point O. Very similar fashion, we can also measure the solid angle. If we say that this is the surface, so this is going to have a surface area. So if this is the surface area and this distance is r, solid angle can be measured as surface area divided by r square. Just like we say that the arc distance, arc length divided by radius is theta, in a similar fashion, surface area divided by r square is omega. It's read as omega. This is L by R dimensionless entity. In a similar fashion, this is surface area by r square. Again, it is dimensionless entity. Because surface is meter square and this meter square will make it this. So this is also just like plane angle, dimensionless entity. Now, let's talk about it in the form that we are going to use in this cluster and all. This was regarding basic understanding about solid angle. Now, what we do in a plane angle? Suppose we have this L length and this is point O. So let's do this kind of construction. This is point O, and the line coming from this point O, it is making 90 degree from this, this line AB. This is length R, and let's say this AB is delta L. So if this kind of scenario is, we measure this angle theta. How? This theta will be, or let's call it delta theta. So this delta theta will be what? Delta theta will be delta L divided by R, just like extension of the discussion that we have just finished. So if we have delta L perpendicular to the direction line coming from O, then we say that delta theta is delta L by R. Now, if we change the case by little, okay, I'm just trying to make a distinction, so I'm just using different color here, so that we don't confuse which one is what. This AB line is the arc, or let me say this is the curve. Now, let's say we are interested in finding out this angle theta for a plane case itself from a point O, the similar setup. But this time, what is happening? This L delta L is not perpendicular to this. That means it is, let's say, inclined by some angle. So this is now delta L. So we are saying that this is point A, this is point B. What we will be doing basically, we will be learning this point, learning this point. This outward normal of, or the positive normal of this given curve will be N. Let's say this makes an angle alpha. This makes an angle alpha from the direction which is horizontal this direction. And this is our delta L. If this case is given to us, can we find out what will be this theta or delta theta? I'm just talking about the plane angle again. And then we'll be extending this correlation for the solid angle. Here, let's try to make a correlation. This length is, or this is R. Here what we did, we used the length which was perpendicular to the line that was coming. That was, if that is delta L, so delta L by R is the delta theta. But here, things are different. That means the curve is inclined by some angle alpha. So what we will be doing, we will be making this curve in this manner. Perpendicular to this. If we do so, its positive normal will be pointing in this direction. Its positive normal now will point in this direction. So what will be the length of this, which is perpendicular or which is in the direction of the line coming? So can we say that this will be delta L cos of alpha? Why? Because this is n vector, so this vector will be n cos of alpha. If this is delta L, so this component will be delta S cos of alpha. So that means if the surface or if this curve is inclined by angle alpha, then delta theta in that case will be using delta L cos of alpha by RC. So if we have inclined curve by certain angle, then the length of that will be multiplied by cos alpha. This is what happens when we measure the plane angle. Now similar kind of thing we have to extend for solid angle. There also we will have this kind of scenario. Why we are doing all these things? Let me give you a certain idea. What happens that sometimes electric field direction is known to us in certain directions. And maybe we can have the direction of this surface in another direction. So that means the surface may not always be in the same direction as the electric field. It may be inclined at certain angle, just like this is inclined here for two-dimensional plane. If it is happening in surface area, then solid angle will be correspondingly changing. So let's talk about the solid angle, and when we will be talking about this, it will become more and more clear. So if we say that we have this as a surface. This is, you can say, circular ring or circular or whatever, circular surface. So based on this, if we try to find out the solid angle at certain point, so that solid angle will be measured by this, all the points on this. It's not looking very right, so let me make it properly. Yes, some sort of this. So this is surface delta S. Now this delta S has a direction, its positive normal is in this direction, which is in the direction of the line joining this point or this horizontal line. So this time, if this angle is omega or delta omega, we can write this angle, so this is R. I hope it's visible. So delta omega will be delta S by R square, based on the formulation that we have discussed. So in this case, we will have this kind of scenario. Now, it's not necessary that we have the surface almost aligned in this fashion. It may be inclined just like this curve was inclined. In that case, what this solid angle will be? Delta omega. What the solid angle going to be when we have inclined surface? So let's say the surface is inclined. That is, it is something like this. Yes. And still we are trying to measure the solid angle from this direction, this point 4. So this will be, I'm just drawing outer points. In other points, it will not be feasible to draw all the points. This time, this is delta S. But what is happening, what's the difference over here is that the positive normal of this surface is in this direction, which is making an alpha angle from this direction, reference direction. So if we try to make a component of this delta surface, delta S surface area, which is towards this direction. So what that will be? Whether we will have a cos alpha factor over here. Another vector will be in perpendicular direction. We are leaving just like we left over here. Or in other words, what we did here, we made the component of this curve. One is horizontal, another is vertical. So this is vertical and another can be horizontal. Since we are not worrying about horizontal, we have left it. We consider only vertical ones. Similarly, we can make the components of this surface as well. So one component will be coming in this direction. Something like this. This will be, its positive normal will be horizontal in the direction and cos alpha. Or we can say this will have a surface delta S cos alpha. So in this case, what will be the solid angle that will be here? It can be written as delta S cos of alpha by R square. So this is a general case we are taking. Here we have considered a particular case. That means where if we are measuring this angle with respect to O, the surface is having positive normal in the line joining this. But this is just a particular case. Here we have considered a general case. That means, depending upon this alpha, it can be made this. If we make alpha 0, so this case is there. And for different values of alpha, it will have a different surfaces. Right? So this is our general result for a solid angle. So for any surface delta S, we can find out the angle created by that surface at any point at a distance r from that as delta S cos alpha by R square. Where this alpha is the angle which is shown in the figure. So this is just direct correlation and generalization of the plane. So whatever I have written over here is plane angle. And whatever I have written in this line, bottom one, is solid angle. Both are similar to a last extent. So plane angle, they are written like this, while solid angle, they are written. After understanding this, let's move ahead. So here we have, this is the final and generalized case that we have, and that we need to remember. Rest is just the supporting for this discussion. Finally, we got solid angle for general case. In general or general case, then it will be delta omega is equal to the surface into the cos alpha divided by R square. This is the solid. Now, let's talk about, or let's have certain observations. Again, we need to compare it with the plane angle. In plane angle, we discussed that theta or delta theta is delta L by R. Now, if the curve is closed, so let me talk about this. Since this delta L was arc, delta L is arc length. So if you are interested in finding out what will be the total angle that will be created at point O, if we complete the whole circle. So the total angle, what will be the total angle? So total angle can be written as, if it is theta, it will be the periphery of that, okay, or the perimeter of this circle, complete arc divided by r, or that means twice pi r divided by r, or that means 2 pi. It simply says that 2 pi is the angle which will be made by a closed curve. So whenever we have a closed curve, complete curve, it will be 2 pi plane angle that can be extended or that can be created at any point. Now let's talk about similar thing regarding solid angle. So what will be the solid angle that can be formed if the surface is closed? This is for closed curve. Let's surface is closed, what is going to be the total angle? Now let's consider this to be a surface. So if we are talking about the solid angle, we have two choices. The first choice is that we can measure the solid angle from any internal point O. We can also measure the solid angle from any external point O prime. This is internal and this is external. So what we are talking about here, this was our internal angle, total internal angle. So let's talk about total internal angle in solid case. So first we are talking about internal angle. What the total internal angle is? Since we know that if we consider a sphere, in that sphere we will have delta S by R square as the